For several months during 1973, astronaut scientists will live and work in the spacecraft called Skylab, conducting a multitude of experiments designed to provide man with a better understanding of himself, his planet, and his universe. Perhaps the most exciting data being anticipated by the large group of experts known as principal investigators concern the resources of our own Earth. Special equipment aboard Skylab will provide a vast amount of new information about the land, sea, and atmosphere. This information will be analyzed by scientists from government agencies like the Departments of Agriculture and the Interior, the National Oceanic and Atmospheric Administration, as well as universities and research institutes here and abroad. The anticipation awaiting the Earth resources data is matched by the expectations of those concerned with another group of experiments aboard Skylab, the solar observations. On Earth, our study of the sun is severely limited by the screening effect of the atmosphere, which scatters the visible light and absorbs much of the infrared and almost all of the ultraviolet and X-ray emissions from the sun. This view of the sun, as seen from the Earth, thus shows but a small fraction of the solar activity that is the source of all our energy. To provide a better understanding of the generation and transmission of this solar energy and its effect on the Earth, Skylab carries a cluster of telescopes that will observe and photograph the sun as never before seen by man, clear of the Earth's atmosphere. Powered by solar panels and mounted in a movable canister, the entire telescope assembly is aimed and operated by the crewmen inside the spacecraft, simulated here by an instructor. Using TV monitors and console controls, the astronauts can pinpoint areas of interest and targets of opportunity on the ever-changing sun. For the first time, we will be able to photograph and measure detailed solar activity, not only in the visible and infrared regions, but also in the ultraviolet and X-ray part of the spectrum. From this information, we expect to gain a far better understanding of the sun's variable effects on the planet Earth, its weather, resources, and people. The solar observations and the Earth resources experiments aboard Skylab have one ultimate purpose in mind: to improve man's lot on Earth. Of the total time devoted to the conduct of the non-medical experiments aboard Skylab, the crewmen will spend about 70% just on the Earth resources and the solar observations. These two groups of investigations, which promise such direct benefits to mankind, will be examined here in more detail, beginning with the Earth resources experiments. Skylab will conduct extensive Earth resources experiments on 65 planned orbits, spaced over an 8-month period to study seasonal variations. The orbits are planned in advance so that Earth resources data collected by Skylab on selected areas called truth sites can be coordinated with similar data from ground-based units, aircraft, and unmanned satellites. With man in the spacecraft, this coordination can be adjusted easily to accommodate weather conditions and other factors affecting the data. Updates from mission control are received prior to each Earth resources experiment and include settings for an array of 6 cameras that photograph the same ground area simultaneously, but in 6 different parts of the visible and infrared spectrum. This is done by using various film and filter combinations for each camera. The value of multispectral photography for Earth resources studies has expanded rapidly in recent years. Aerial photos like these, when exposed to different parts of the infrared spectrum, reveal features and characteristics not readily visible in normal light. Such techniques have been used extensively to gather data on agriculture, mineral deposits, geological features, wildlife, water resources, and a host of other applications. The multispectral cameras aboard Skylab will provide resolution of ground features considerably better than those taken by previous astronauts in orbit around the Earth. Shooting through a special window at the bottom of the multiple docking adapter, the camera assembly is rotated during each picture-taking sequence to compensate for Skylab's forward motion. All 6 cameras shoot the same area at the same time, covering a patch of Earth 88 nautical miles square. A small portion of each scene is also covered by a single large camera with higher resolution located in the orbital workshop. This Earth terrain camera will help to pinpoint areas of particular interest. For the 6 multispectral cameras, operating data such as shutter speed, pictures per sequence, and interval between pictures is recorded on magnetic tape for later analysis. This tape recorder also records all non-photographic data from the other Earth Resources experiments. The recorder, multispectral cameras, and related experiments are checked out and sequenced by a compact control and display panel. The crewmen can set up in advance 1 or more experiments to run concurrently. Ordinarily, several Earth Resources experiments are conducted at the same time, since they are designed to complement each other. For example, the infrared range of the multispectral photography overlaps into the range covered by 2 infrared sensing devices. One of these, a spectrometer, has a telescope that allows the crewman to find and track a pre-planned truth site. A 16-millimeter sequence camera on the telescope records the ground scene viewed by the crewman. The primary data from this spectrometer, however, are non-photographic digital measurements, which are recorded on the magnetic tape. At any one moment in time, the spectrometer reads a minute sample of the scene below, accurately sensing the reflected energy in 2 distinct bands of the near-infrared region. As a rule, simultaneous readings will be made at the truth site itself. This ground truth data will provide specific temperatures and other readings to which the spectrometer measurements can be correlated. This spectrometer is so precise that we may be able to measure temperature and water vapor at various levels in the atmosphere above the site. Thus, the effects of atmospheric absorption may be separated from data obtained by other Earth Resources experiments, such as the multispectral scanner. This scanner also senses energy reflected from the ground, but extends the coverage of the previous experiments into the region known as thermal infrared. Thermal infrared is present whenever bodies emit heat, that is, when they release energy previously absorbed. The multispectral scanner is hard-mounted to provide ground coverage along the flight path directly below the spacecraft. Each data scan covers an area roughly the size of a football field. The reflected energy is sensed simultaneously by 13 detectors in the scanner, each sensitive to a different spectral band. The measurements are recorded as digital data on the magnetic tape. This data can be processed later by special computers to provide ground images and various combinations of the spectral bands recorded. This image was reconstructed from scanner data taken at a Denver test facility. A major task of the principal investigators will be to correlate the data from the multispectral scanner, the infrared spectrometer, the multispectral cameras, and the truth sites. Analyses resulting from the combined data should tell us many things: temperature conditions in coastal waters, sewage outfall and other pollution, size, distribution, and health of agricultural crops, moisture measurements for planting, and flood control. A treasure of data covering vast areas of the Earth. There are limits, however, to the use of infrared and photographic devices for surveying Earth resources, for they cannot penetrate fog or clouds to any useful extent. For this and other reasons, Skylab will carry 2 microwave radars that operate at wavelengths capable of penetrating cloud formations. One of these experiments uses a trainable antenna mounted under the multiple docking adapter. This is a dual-mode antenna that can operate as either a passive or an active radar instrument. In the passive mode, it operates as a radiometer, measuring microwave emissions from both the surface and the atmosphere. In the active mode, it transmits its own energy and detects that part of the return which is scattered back from the ground. Both the active scatterometer and the passive radiometer will be operated together in sequence to cover large areas below the spacecraft and off to the side. Sea and ice conditions, even in remote areas, can thus be monitored under all weather conditions. At other times, the active radar will also be used as an altimeter, pointing straight down to monitor distances from the surface. The second microwave experiment is another passive radiometer with its antenna hard-mounted under the forward end of the multiple docking adapter. This radiometer operates at a longer wavelength and will detect emission energy in the L-band region. Here again, the microwave experiment should tell us many things about our Earth resources: surface conditions of the ocean, fishing beds, salinity distributions in river deltas, sea and lake ice, snow cover, soil moisture content, and seasonal vegetation changes, among other things. Most important, all of these Earth resources experiments complement each other so that the value of any one experiment is greatly enhanced by its coordination with other data. And with man aboard, these same experiments can be adjusted rapidly in response to conditions not predicted in advance, such as hurricanes forming. In its 3 manned missions, Skylab will record a massive amount of information on our Earth resources, including about 33,000 separate photographs and 25 reels of magnetic tape containing billions of bits of data. At the end of each Skylab mission, the tape and film data will be transferred to the command and service module for the return to Earth. This data, along with crew comments, will be processed by the Johnson Space Center in Houston and reproduced for distribution to the principal investigators and their working teams. They will perform the data reduction and analysis and publish the results. Much of this work will take considerable time, but some quick-look data will be available in time for the next Skylab mission so that the Earth resources experiments can be used as effectively as possible. Now, having viewed the Earth, we turn our attention to the Sun, as Skylab will do, for the solar observations. Viewing the Sun from ground observatories, the principal investigators find more questions than answers in the solar phenomena. What is the nature of the Sun's nuclear activity? Can it tell us the secret of controlled atomic fusion and teach us how to provide unlimited quantities of clean power on Earth? As the Sun transmits energy to us, how do the sudden flares affect our long-range weather cycles? The answers to these and many other questions may be locked in those areas of the Sun where temperatures are so high that all elements present are ionized, generating extreme ultraviolet and X-ray energy. Yet this information cannot reach Earthbound observers because of the screening effects of our atmosphere. This is why the principal investigators wait anxiously for the Skylab data. For Skylab includes among its experiments a complete solar observatory that will view the Sun from outside the Earth's atmosphere. The telescope assembly, with its power-generating solar panels, is deployed after the spacecraft reaches orbit. The assembly consists of 8 telescopes mounted in a movable canister that is controlled remotely by the astronauts inside the spacecraft. A thermal control system maintains the telescope assembly at a constant temperature. When taking data of solar activity, The assembly is automatically locked on the sun and isolated from minor movements of the spacecraft itself. Operation and fine pointing of the telescope assembly are controlled at a console inside the multiple docking adapter. Specially scheduled solar observation programs will be coordinated through mission control in cooperation with ground observatories throughout the world. These scheduled programs include the launching of rockets bearing instruments similar to those on Skylab. Planned observations will be updated frequently by mission control because of the transient nature of solar phenomena. Except for Earth resources orbits, the Skylab will normally be placed in a sun-oriented attitude with the telescopes and solar panels constantly facing the sun. Prior to each solar observation, the astronaut sets up the control panel to place the appropriate telescope experiments in ready condition. Here again, the experiments are designed to complement each other so that normally several will be run at the same time. For the solar observations, almost all data will be recorded on film. The cameras are located inside the canister as part of the telescope assembly. For coordination and quick interpretation, some data will be transmitted to Earth as it is happening, particularly during the specially scheduled programs. Normally, however, such data will be recorded for delayed transmission. One big advantage of this manned space observatory is that the crew can point the telescopes with great accuracy at any point on the solar disk or the space surrounding it to collect data on unforeseen solar phenomena. For this purpose, the crew uses a closed-circuit TV system that can select images from 5 different telescopes. 2 of the telescopes operate at the extreme red end of the visible spectrum, like those on the ground. These are used to coordinate areas of interest and primarily to point the entire telescope assembly. The telescopes can be rolled and pointed with controls on the console to line up a particular feature for observation. There are 6 different experiments in the solar observations, each designed to record data of a particular character. For example, the corona that surrounds the sun is important because it is a signature of the way energy is being transmitted from the surface. One of the Skylab telescopes, called a white light coronagraph, will enable us to see the corona far clearer than ever before, using occulting disks to create an artificial eclipse. For the first time, we will be able to see the outer corona far into space, undistorted by the atmosphere. Further, during Skylab's 8-month excursion around the sun, each of the crews will take thousands of photographs to provide a 3-dimensional survey of the corona. The other solar experiments will provide the all-important coverage in the ultraviolet, extreme ultraviolet, and X-ray portions of the spectrum. Since the ultraviolet experiment does not generate an image of its own, it uses one of the other telescopes for spotting. Here, the experiment measures the intensity and distribution of solar energy in the ultraviolet region, providing digital data at 7 different points of the spectrum. This data is taped for transmission to the ground, where it can be reconstructed to produce images for each of the 7 points in the ultraviolet region. For the extreme ultraviolet region, there are 2 experiments, one providing clear photographic images at different wavelengths, while the other yields precise intensity measurements on a very narrow sampling basis. Within the area indicated by the slit, this experiment can distinguish several different wavelengths in the extreme ultraviolet region. The last 2 experiments cover the X-ray portion of the spectrum, which, like the ultraviolet region, does not reach ground-based observers. Bursts of X-ray energy frequently signal the start of solar flare activity, which is a phenomenon of vital interest to solar observers. These bursts also affect microwave radio signals. Taking advantage of this knowledge, Skylab has a solar radio noise burst monitor to alert the crewmen when flare activity might be imminent. When the alert is sounded, the crew will try to record the event as it occurs. This film has been speeded up. In many cases, a flare may form over a period of minutes or even hours. One of the X-ray telescopes covers the entire solar disk, providing both a photographic image and a display on a special monitor. This experiment also provides measurements of the intensity of X-ray energy throughout the scene. These measurements are fed to a digital display and are also transmitted to the ground. The other X-ray telescope operates in another region of the X-ray spectrum and also provides both a photographic image and precise measurements of the intensity at selected wavelengths. Here again, the intensity measurements will be transmitted to the ground, where a worldwide network of solar observers await. The spacecraft will also transmit at times the same video image being viewed by the flight crew, assuring close coordination. In some cases, the solar observations will be set up for automatic operation, so that the data can be recorded even while the astronauts sleep, or when the spacecraft is unmanned. To recover the film data, two of the crewmen will don their spacesuits, depressurize the airlock, and while one awaits at the airlock entrance, the other will exit to remove the film cassettes from the canister. During the same excursion, all cameras will be reloaded with fresh film. At the end of each mission, the exposed film will be transferred to the command and service module for the return trip to Earth. There will be sufficient time after each mission to make a preliminary review of the film data and to revise the solar observations accordingly for the next mission. The interest of many people throughout the world will be riding with the astronaut scientists who man this laboratory in the sky. We have seen here some of the reasons why. In a world dependent upon resources and energy, the Earth resources and solar experiments of Skylab are of global interest.